Make sure your name, date, and class period is in the top right-hand corner. The title of this note is Mean Value Theorem. And we are studying the mean value theorem because it's an important connection between the average and the instantaneous rates of change. If you remember back at the beginning of the year, we talked a lot about the average rate of change and the instantaneous. Remember, that's just another word for the derivative. So first, we're going to copy the text of the mean value theorem into our notes. So the criteria is that the function must be continuous on a closed interval. Must be continuous on a closed interval. That's the same criteria for the extreme value theorem. There's an additional piece of criteria. The function must be differentiable everywhere on the domain. You can't be differentiable at endpoints, which is why that's an open domain from A to B. So what we see here is this equation. And this is the derivative, or the instantaneous rate of change. Not sure if that's how to spell instantaneous. Instantaneous rate of change equals, over here, that's really the slope formula. Which is a way of calculating the average rate of change. So what this mean value theorem is saying, mean as an average, it's saying that the average rate of change equals the instantaneous rate of change at some point. There's at least, it can happen more than once, but there's at least one place where the average rate of change and the instantaneous rate of change are the same. So we're actually going to look at an example of this. So the example is the function f of x equals x squared. So that, and we're going to look at the interval, closed interval 0 to 2. So we have a closed interval, it's continuous from 0 to 2, and it's differentiable from 0 to 2. So it meets all the criteria of the mean value theorem. So f of x equals x squared on the interval 0 to 2. It's closed. It's continuous because it's a parabola. Is it differentiable? Well, the derivative is 2x, and 2x is a line. A line is continuous, so it is differentiable. So it meets all the criteria of the mean value theorem. So what we're going to do is we're actually going to figure out where this point C is. So first, let's figure out the average rate of change. I'm going to use a delta symbol for change. Average rate of change from 0 to 2. So that's saying, what are you at 0 and what are you at 2? So this function at 0 is 0, and the output at 2 is 4. So we see that we have a change of 4 units over 2 units. It's really just saying what's the slope, what's the change in the outputs divided by the change in the inputs. This value here is actually 4. This value here is actually 0. So we have 4 over 2, which simplifies to 2. The average rate of change is 2 from 0 to 2. So what the mean value theorem says is that there is some place where the derivative of the function equals the average rate of change. And that's exactly what we're going to find out. We're going to find out where that place is. We're actually going to use the letter C. There's some derivative, there's some point C that has a derivative of 2. So the derivative of the function is 2x. And we want to know, hey, for what value of x is the derivative equal to the average rate of change? So doing a little algebra here, we see that at 1, the derivative of the function is 2, which was the average rate of change. And notice that 1 is in the interval from 0 to 2. That's what the mean value theorem says. That answer has to be on that interval. So I'm actually going to show you a graph of what this looks like. So here is, in blue, that's the graph of x squared. Okay, and the average rate of change is represented in black. It's just a line segment. So that line segment has a slope of 2, right? It's the rise over run, 2 over 1. So we have a slope of 2. And we notice that there is a point where the tangent line also has a slope of 2. All right, so there are a couple of other topics in this unit besides the mean value theorem. So let's think of some functions that have a derivative of 0. So off the top of my head, I'm thinking that if f of x equals 1, then the derivative is 0. If f of x equals 2, then the derivative is 0. If f of x equals any number, c for constant, any constant number, then the derivative is 0. What about functions that have the derivative of 2x? Well, I know x squared has a derivative of 2x. But is there anything else? What about x squared plus 1? Remember that when you're finding the derivative, you take the derivative of each piece. The derivative of x squared is 2x, and the derivative of 1 is 0. So that also has a derivative of 2x. So we can add a number, any number at all, I'm going to call it c, and it will have the same derivative. So that's going to be important for us when we're talking about antiderivatives. So the antiderivative is the opposite of the derivative. We're going to use the symbol capital F for antiderivative. So capital F is an antiderivative, and the definition of an antiderivative is that the derivative of an antiderivative is the original function. And when you're finding an antiderivative, the process you are engaging in is called antidifferentiation. So let's look at an example here. All right, suppose we want to find the velocity and position of an object, and we know its acceleration. So remember that we have position, velocity, and acceleration. And each one is the derivative of the next. So if we call position f, the velocity is the derivative of f, and the acceleration is the derivative of the derivative. It's called the second derivative. So now we're going to work backwards. We know that the acceleration is a single number, 9.8. So we want to find the antiderivative. I'm just going to label this one acceleration. We want to find the antiderivative. So the antiderivative is capital F. And we know that the derivative of capital F has to be 9.8. So the antiderivative of 9.8 is going to be 9.8x. And you can check this by taking the derivative. Take the derivative of capital F. It's 9.8, which equals the function that we started with. And remember that that was your definition of an antiderivative. The definition of an antiderivative is that the derivative of an antiderivative is the original function. So if the acceleration is 9.8, then the velocity is 9.8x. And then we also want the position. So the position will be the antiderivative of the velocity. So now I'm going to, actually I'm going to use let me not use f, I'm going to use g. G of x is my velocity. and I already solved it. It's 9.8x. So I want the antiderivative, so I'm going to use the capital letter, the antiderivative of 9.8x. Okay, so let's think about this. 9.8x has an exponent of 1. When you're taking the derivative, the exponent decreases by 1. So for the antiderivative, the exponent will increase by 2. Put the 9.8 in front. Also, when you go to take your derivative, remember you're going to be multiplying 2 times 9.8. So we need to do the inverse and divide. So this is the antiderivative, 9.8 over 2 x squared. And we could simplify that if we wanted. 9.8 divided by 2 will be 4.9 x squared. That is the antiderivative of 9.8x. Again, you could check it. You could do the derivative, multiply 4.9 times 2, you get 9.8x, and then subtract 1. X to the first power. So we do check, and we see that we get the derivative there. So this now would be my position function. All right, so we just covered 2 major ideas, mean value theorem and anti-differentiation. This will be it for our notes, and we're going to be adding more information to this in class.